Fermi is an observatory designed to see the most extreme places in the universe. We see gamma rays, which are the highest energy form of light. And with each object that we see these gamma rays from, what we're doing is exploring some of the places in the universe with the most extreme environments.
The kinds of objects that we can study are pulsars and neutron stars, black holes, as well as dark matter. The main challenge in detecting gamma rays is that the Earth's atmosphere is opaque to them. So to get around that, we use satellites in space to measure gamma rays.
We don't have lenses and mirrors because gamma rays would just go straight through them. The main instrument on Fermi is the Large Area Telescope. It's a telescope that detects gamma rays by converting them into electron-positron pairs. Those are charged particles. So fundamentally, our detector is designed to measure the tracks of those charged particles moving through, and from that figure out where the gamma ray came from. The problem is that in the environment of low Earth orbit, there's a very large number of charged particles. So for every gamma ray that we detect, 10,000 charged particles are coming through our detector. So we have to be able to tell the difference between that one gamma ray from those 10,000 charged particles. And that's a challenge. Often, they deposit a large amount of energy and stuff splashes up in all directions, and you end up with extra hits in the tracking part of the detector that are not actually from the original electron and positron, but rather from energy that's kicked up when they interact further in the calorimeter.
So, to analyze these events, we have written a very long and complex program that basically uses all the information that was recorded by the instrument and figure out what is the direction of the gamma ray, its energy, and whether or not it's a real gamma ray and not a charged cosmic ray. So obviously software is really important for the LAT.
The software that we use to analyze the LAT data has gone through many revisions over the course of the mission, but PAS-8 is really the first revision of the software where we took into account all of the experience that we gained from operating the LAT in its orbital environment.
PAS-8 has given us the equivalent of an in-space hardware upgrade, but on the ground.
We've increased the sensitivity of the LAT instrument by 40%, and this is roughly equivalent to launching another LAT instrument and operating it as well for 7 years. So it's a fairly substantial improvement in the LAT performance.
The most immediate kind of shocking benefit of PAS-8 is our ability to view the sky at high energies where we have particularly improved our angular resolution, so the sharpness is very evident, and we've added lots more gamma rays, so we filled in what was kind of a spotty sky. PAS-8 has made everything better, but one of the things that it's made better is that it's allowed us to open our gamma ray eyes to higher energies before, so that's a completely new view, and it's allowed us to open our gamma ray eyes at energies lower than before, so that's another completely new view, in addition to improving everything across the entire energy range. We have a wider field of view. We see more photons from any given point in our detector than we did before.
The improvements that we've made to the software retroactively apply to all the data that we've collected. And so these improvements significantly enhance what we can do with the data that we already have, as well as the data that we'll collect in the future.
With PAS-8, we're able to go back to the sensor by sensor information, and we can reprocess that data into the improved performance that we get with PAS-8 from the first day of the mission, from August 2008, right the way up to the present day.
So with PAS-8, we use more completely and more efficiently all the information that is recorded by the instrument. One thing that I like is that these photons it took a lot of time to come to Earth, so that it's a pity to just miss one of them. So I'm glad that with PAS-8 we're more efficient and we record every gamma ray that's passed through us.
Look, obviously I'm biased. I do think it's really cool. And when I first started working on Fermi, and you start and think, oh, how does this detector work? And then you think more and think more and think more about it. This is really cool. This is really cool even if you weren't doing any astrophysics with it. And then you add the astrophysics and it's awesome.